All right, so here we go. So yesterday, we ended the hour talking about inertia and mass. All right, so remember that our physics definition of mass is a measure of inertia, which only makes sense if you know what inertia is. And inertia is, remember you guys, it's a property of matter. If I give you an object, no matter what you do to the object, that object has a fixed amount of inertia. All right? And that inertia is its resistance to a change in motion. All right? And the idea is objects with more mass are more resistant to a change in motion. Which is why if a semi-truck is rolling at you, it's much harder for you to stop the semi-truck than it is to stop a skateboard, right? That is why it is easier to get the skateboard moving than it is to get the semi-truck moving. It's easier to turn a skateboard if you don't worry about the balance thing. It's easier to turn a skateboard than it is to turn a truck, right? Because the skateboard has less inertia. It is less resistant to a change in motion because it has less mass. Cool. So the definition is a little bit circular. Basically what you need to know is that inertia is determined by mass. Cool. All right, that will become more apparent as we go through the examples today. So, are we all good with that? Yes. Dynamite. Okay, so these next two slides basically say what I just said. So, there you go. All right, so in the past, when I had to teach physics to like freshmen who struggle with math, which weirdly happened in my old district, I would tell them this. Here's basically what Newton's second law says. All right, this is a little bit oversimplified, but this is the gist of it. Remember, Newton's second law says acceleration is net force over mass, right? So it's saying the harder you push something, the more it'll accelerate. The harder you push something, the more it will accelerate, right? And the more mass it has, the less it's going to accelerate, right? Okay. So that's a little bit sloppy because it sort of overlooks the whole net force thing, right? It's just talking about the force that you exert. All right. So more sort of scientific. I see a lot of you writing this down, so wait a second. In a minute, I'll give you a sort of more mathy presentation of that same idea. Everybody up to speed there? Okay, so here's the same thing, just a little bit more, like I say, a little bit more mathy. So a lot of times, like if you look up Newton's second law in a lot of textbooks, instead of just giving you an equation, so if you asked me what Newton's second law is, I would just say this: acceleration is net force over mass. Okay? The sort of technical way of stating is this: an object's acceleration is directly proportional to the net force on the object, and inversely proportional to its mass. More force gives more acceleration, more mass gives less acceleration. All right. So we're going to walk through a few examples. The first sort of 4 examples I'm going to go through really quickly. They're basically just designed to mathematically kind of help you understand this. All right, and then there are 2 examples that'll be a little bit more similar to what you'll see in the homework. Okay. Any questions before I go on? Until everybody's done writing. I'm struggling this week. I just feels like I can't get enough energy to get going for some reason. All right. No, a couple people still writing. Okay, everybody good? All right, so, kabam. All right, so there are 4 little examples here. I don't know that you need to write out the whole scenario. Basically, what you need to know is in each of these 4 scenarios, Roy's going to be pushing a box across a frictionless floor, okay? And in each of the cases, we've got a different mass for the box and a different force that Roy is exerting, okay? So in our first example, you probably can't see it, but the mass of the box is 4 kilograms, and Roy's force is 12 newtons. So rather than write it out, let's just draw it. So here's our box. The mass of the box is 4 kilograms. Remember, that's going to be my norm. I'm going to always write the mass of the object inside the box. Okay? And then draw your force of Roy. It's 12 newtons. All right? And that alone is enough to find our acceleration, right? Acceleration is net force over mass. So, because our floor is frictionless, and Roy is exerting 12 newtons of force, our net force is going to be 12 newtons, right? And the mass is going to be 4 kilograms, right? So divide it out. 12 divided by 4, it gives you 3. We talked yesterday about the fact that a newton is the force required to move 1 kilogram at 1 meter per second squared. So your kilograms cancel and you're left with meters per second squared. Good? Right, so not rocket science, I get it. So, but what we're going to do now is, now that we've done this sort of part A, we've got these 3 other parts that we're going to do. So in each part, what's going to happen is we're going to change the force of the mass, or maybe both, and we're going to compare it with this first case. Okay? So this is sort of our base case, right? Moving over here to part B, we're going to push the same 4 kilogram box, but we're going to push it with twice as much force, right? Our force is going from 12 newtons to 24 newtons. Okay? So let's see what happens. So here's the box. It's still a mass of 4 kilograms, but now my force is much bigger. Notice that I drew that arrow longer to indicate there being more force, right? So now when I find the acceleration, it's net force over mass, but we got a bigger force on the same mass. More force on the same mass gives you more acceleration. Specifically, what happened to the force here, you guys? Doubled. And what happened to the acceleration? Doubled, right? So the acceleration is proportional to the net force. Cool? All right. So going down here to see, instead of doubling the force, let's try doubling the mass and see what happens. So I'm going to go back to 12 newtons, but instead of using the 12 newtons to push 4 kilograms, I'm going to use the 12 newtons to push 8 kilograms. So let's draw this. Here we go. Here's the box. Draw the box bigger. Oh, does that look bigger? Pretend that looks bigger. All right, so here's our mass. Here's our force of Roy, 12 newtons. Now we can find our acceleration, net force over mass. So the idea is Roy's still pushing with 12 newtons, but now instead of trying to move 4 kilograms, he's moving 8 kilograms. So you're dividing by a number that's twice as big, and the result is half as much acceleration, right? So our acceleration went from 3 down to 1.5. It got chopped in half. Cool? Okay. So in terms of inertia, in object, or in part A, our inertia was sort of like 4 kilograms worth of inertia, right? In the next one, our inertia was sort of 8 kilograms worth. And the idea is, because we have more inertia, we got less acceleration. So this object here resisted a change in resisted a change in velocity more than the other one, right? Because it has a smaller acceleration. Cool. All right, everybody good with C? All right, and then in D, what's going to happen is we're going to go back to this base case. We're going to double both the mass and the force. So what ends up happening? Yeah, you get the same acceleration you would have had, right? You're moving twice as much, but you got twice as much force to do it, right? So our mass is 8 kilograms. Our force of Roy is 24 newtons. And so our acceleration, net force over mass, 24 newtons over 8 kilograms, and you're back to 3 meters a second squared. Follow? Any problems with it? Okay. So, some of you are kind of rolling your eyes. I get it. I'm really trying to start with keeping this basic. I promise this gets harder. When we get to section 3.6, which will be early next week, we're going to do friction, and the difficulty really ramps up. So please make sure as we're going through this sort of simple stuff that if you're confused about stuff, that you stop me next. All right? So with that in mind, any questions before we go? All right. Well, you guys are quiet today. Oh, shoot. I had a slide there and I deleted it by accident. Okay, so here's the deal. The way the problems are going to be set up, there's always going to be stuff that you don't know, right? You're either going to be missing a force, like the question will say, what was the force of friction? Or what was Roy's force? Or you'll know all of the forces, but then you'll be asked to find out, like, what's the velocity after 8 seconds? Or something like that, okay? So what's going to sort of tie every problem together is this idea that there are 2 ways to find net force and a whole bunch of ways of finding acceleration, okay? So there's basically 2 types of problems, right? So here's kind of a list of equations that we can use, all right? So there's 2 sort of net force equations, all right? In some of the problems, I will give you all of the forces. And when I give you all of the forces to find your net force, well, what's the definition of net force, you guys? The sum of all the forces, the total of all the forces, right? So one way that you can find your net force is just by, if I give you all of the forces, then just add them all up. So take force number 1 plus force number 2 plus force number 3 plus whatever for however many forces there are, right? But of course that only works if you know all the forces, right? If you don't know the force of friction, then you can't add up all your forces because you're missing one of them, right? Okay? So the other way that you can find net force is by doing mass times acceleration, right? But doing that would require that you know the mass and the acceleration. Okay? So let's talk then about acceleration. All right, there are a bunch of ways of finding acceleration. Well, if you know your net force, then you can find your acceleration by using Newton's second law, right? If you, thank you. Yeah, you guys are like, I said I was tired. Man, you guys are worse off than me. All right, if you don't know your net force, then you got to use an old school equation for your acceleration, which means one of these guys. Yeah, right? So from last chapter, or you can use this guy. Or you can use this guy. All right? So all of those equations are still at your disposal. So when you're solving problems, what you're going to want to do is you're going to want to make a drawing. You're going to want to write down all the stuff that you know. Figure out what it is that you don't know. And then find a path using these, whatever, 6 equations. And find the thing you're missing. All right? So I'll tell you, there's usually 2 kinds of problems. There are problems where I give you all of the forces. So you'll use this to find your net force. Knowing your net force, you'll use that to find the acceleration. And then you'll use one of these other equations to find some missing thing, either how far it went, or how long it took, or what velocity it ends up at. Okay? And then there are other problems where you're missing a force. So in those problems, you'll know enough information that you can use one of these guys to find your acceleration. Then once you know the acceleration, you find the net force, and then you use this guy to find the missing force. That was a lot of information at once. I'm going to show you an example of each now. Yes. Yeah. Are those the only equations that you need to know right now? I mean, yeah, obviously you should be able to algebraify any of those equations, for sure. I'm going to say yes right now, but I'm doing it hesitantly because I'm worried that I'm overlooking something obvious. But I think that's it. Can anybody think of anything that I'm missing equation-wise? I don't think so. I mean, you should know how to use vector addition. Okay, so here we go. 2 examples. Here we go. Example number 1. Write it down. If you finish writing it down, draw it. If you finish drawing it, do some calculations. See if you can find the velocity of the box after 3 seconds. I'll go over it in a second. See how far you can get. Yeah. Good work. I'm going to start drawing while you guys work. For box mass equals 15 kilograms. Force of Roy equals 120 newtons. Which way is friction going to go, you guys? Opposite direction that Roy pushed it. Now notice, the problem didn't tell us which way Roy pushed it, right? So it's apparently not important. So in that circumstance, just assume that he's pushing it forward. All right? But what you know is, since he's pushing it from rest, friction can't stop it from moving, so friction's going to go the other way. All right, we also know that our initial velocity is 0. We know he's going to push it for 3 seconds, and we want to find the velocity at the end of those 3 seconds.
Ooh, whoops. I found
I disagree with that statement, but...
No, trust me.
Whoa, you just got called out. All right.
He comes up to me when I'm holding Gatorade water bottles and squeezes.
That is a false accusation.
Yes, it is.
Yes, right. That is a false accusation. I don't do that.
Are you like the throwing Slurpees and things stations, like the bad guys who believe?
I don't know. I can't relate to that.
Oh my gosh. My wife watches it. And I get stuck watching it sometimes.
3 seconds.
Start watching what? Is it still on?
I think somehow.
Some weird incarnation of it. Like, please, acknowledge it. All right, let's get back to this. Okay. All right, so let's come back together, you guys. Is everybody okay with the information that I put on the board thus far?
Yes.
All right. So we're trying to find our final velocity. So the only equations that we have to find final velocity would be either this guy or that guy, right? Using this guy would require me to know the displacement. This one requires time. That one looks probably like a better option. But we also need to know the acceleration, right?
You can get that.
And you can get that. How did you get that, Griffin?
I didn't track it.
Okay.
You use the forces. You can get the net force by subtracting.
Yeah. Good. So we can use the definition of net force to find our net force. Remember, definition of net force is all the forces added up. So far, these are the only forces on the object. 120 newtons from Roy, 30 from friction. So it's the force of Roy plus the force of friction, 120 newtons plus negative 30 newtons. So our net force is 90 newtons. Oh, that's not what I wanted to do. All right, so is everybody okay with how we found our net force? Now that we know our net force, what can we do? Divide by the mass to get the acceleration. So you need to be, in your head, you need to be thinking the acceleration is determined by the net force, and the net force determines the acceleration. So at some point in your problem, you're going to have to either use net force to find acceleration or acceleration to find net force. Every problem. That's what connects chapter 1 to chapter 3, is that one equation. All right? So now we can go, oh, acceleration is net force over mass. So the net force, notice, is 90 newtons, not 120. Our mass is 15 kilograms. Divide it and you get 6 meters a second squared. So now we can find our VF. Everybody okay with this equation? That's the acceleration equation rearrangified. So our VI 0, acceleration we just found at 6. Time was what, 3 seconds? So we get 18 meters a second.
You have to show all that work.
If you don't show all that work and you get a wrong answer, you won't get any partial credit. So
Like, if you like tap into it in your head,
as long as you get it right, the problems are going to get harder though. So. All right, are we good up to here? Everybody's happy, yes? All right, last example. All right, so now we got a 12 kilogram box. It's sliding. This one's a little bit tougher, but still we're not getting too crazy yet. But, you know, make sure you understand it. If I lose you anywhere, stop me. So we got a 12 kilogram box that's sliding horizontally at 18 meters a second across the floor. He wants to slow the box down to 4 meters a second in 2 seconds. There's already 24 newtons of friction. So the question is, how much force does he have to exert and in which direction? Notice, we don't know what direction he's pushing. Maybe the 24 newtons would stop the box in 1 second, or would slow the box down in 1 second. You know what I mean? Like maybe he needs to push it forwards so that it slows down more gradually. You see what I'm saying? Like if he wasn't there, friction would slow the box down, right? And so he wants it to do this specific thing. He wants it to go from 18 to 4 in 2 seconds. And so the question is, how much force does he need to exert? And in which direction? Does he have to help friction to make it slow down faster? Or does he have to work against friction to make it slow down slower? It is clutch. So, make a drawing, see what you can figure out. All right, so let's start drawing this thing. Holy cow, we're taking longer this hour than we did last hour. So there's our 12 kilograms. We know that the initial velocity of the box was 18 meters a second. We know we want the final velocity to be 4 meters a second. We know the time is 2 seconds. If we assume that the box is moving this way, which way is friction going to go, you guys? Other way. All right, is everybody good up to here? What's wrong, Tyler? What's up? Gotcha. All right, so my net force is negative 24, right? No, why not?
I mean, it's not, that's something that.
Yeah, that's not the net force. We don't know the net force because we have a missing force. We don't know Roy's force. So our net force is Roy's force, whatever it is, plus negative 24. So we got to find our net force. Does anybody see a way to do it? Find what? Solve for x, is that what you're saying? What is x? No, you're right. Go ahead and finish your thought.
Wow. If you know the other forces, you can put it into the net force equation
Okay.
and like solve and try to find out yeah.
Okay, but so for that to work, we need something else first, right? Like, we need to know our net force, right? So have you got an idea about how to find it, Taylor?
Yeah, so I put it into the acceleration equals net force plus mass, and I rearranged it so it's acceleration times mass.
Cool. So you guys are all knocking on the door, but we're still missing something else. We can't do that until we know the. We got Camilla.
Acceleration first.
Yeah, we got to get the acceleration, right? I'm sorry.
Oh, shoot, I'm not.
Yeah, we haven't done that yet. All right, so that's okay. All right, so find your acceleration. Oh, cool. You guys are like hostile today.
I am crazy.
Goodness.
It's gonna be like that. Exactly. So it's and it's 7.
All right.
I think I did not.
All right, so we find the acceleration. It ends up being -7. That we know that has to be the acceleration because we need our velocity to get down to 4 from 18 in 2 seconds, right? All right, so now we can do what Phelan was saying, and we can use that to find our net force. So Phelan said, shh, you guys please. Phelan said rearrange this, which totally works, 100%. And we're going to use this so often that I would just sort of list it as another equation that we know. It's the same thing, just algebraically rearranged, right? And at this point, we know our mass, we know our acceleration, so let's do that. All right, let me free up some space here on the board. It's getting a little bit cluttered. Whoa, that's not what I wanted to happen. That is what I wanted to happen. Okay, so the mass of the box is 12 kilograms. Acceleration's -7 meters a second squared, so our net force is -84 newtons. So, am I done? Is that Roy's force? No, that is the net force. So, please hear me say this. I've been saying, like, I don't care how much work you show. For a problem like this, I want you to get in the habit of doing exactly what Margaret was saying before, which is write it out and solve for x. Net force is the force of Roy plus the force of friction. So for us, we know the net force is -84 newtons. Force of Roy is our x. Force of friction is -24 newtons, and solve it. Because in this one, a lot of you are able to just look at it and go, oh, it's got to be 60. Great. And the problems are going to get more complicated. And a lot of times you won't be able to just look at it and know what it is. So if you get in the habit of doing this now, when we get to harder problems, it'll make things easier. All right? So, how do we solve this, you guys? Add 24 and you get -60 newtons equals your force of Roy. Okay, so there's your answer. And what's the significance of the fact that it's negative? It tells us that he's got to push in the same direction as friction to kind of help it out, right? Make sense? Griffin, what'd you say?
You can push in the same direction as friction.
Sure. Because what's happening is, so the box is already sliding, friction's slowing it down. Okay? But if Roy didn't touch it, it would slow down, but it would take more than 2 seconds for it to slow down to 4. So he's sort of helping friction slow it down. He's pushing in the opposite direction that it's moving, that's correct. With a force of 60 newtons. Good. All right. Any questions? All right. Phones. Put them away. Here's your tests.